Hello guys, welcome back to Maison African Motives, still on engineering science N3, working with moments. So we've got a question from the question paper of November 2020, which is on moments. So the first question we are given 2.1 was to define the moment of a force. So what are we actually having there on the moment of a force? Okay, so the moment of a force can be defined as the force multiplied by the perpendicular distance from the turning point to the line of action of the force, which is the fulcrum. Okay, so that is how we can actually define the moment of a force. That is the force multiplied to the perpendicular distance from the turning point to the line of action of the force. All right, so that's what we had in this case. Let's check the other part of the question, which is on 2.2. We are given Fig A shows a light horizontal beam for a uniform cross-section loaded as shown. Okay, so this is how our cross-section looks like. And we are given now to calculate the reactions of the supports A and D. All right, so let's see what we have. Okay, actually A is a support here, and D is a support also. Okay, so let's check this diagram. I just redrew this part. I just hope it's going to be clear, but it's just the same thing. Or these dimensions, you can just take them down here, 2 meters, these 3 meters, you write it down, these 3 meters, you write it down, these 4 meters, you write it down here. Okay, so I have this diagram. Yes, so we are going to work it from this side so that we can understand what the question is asking us. Okay, so I just did a simple diagram in this manner. So we are given in this case to calculate the reaction of the supports at A and at this point D. Take note, we've got the distributed load of 5 kilonewton and other one of 5 kilonewton at the end as for our diagram here, this 5 and this 5 here. All right, so remember this is important when you are calculating the reactions. Since we are given that this is 5 kilonewton per meter and we're given 2 meters, we're going to multiply 5 by 2, which is 10 meters. All right, so this is going to be 10 meters, 10 kilonewton, sorry. So this will be 10 kilonewton separated between the 2 meters. So if we divide by 2, that means we are going to separate 1 meter from each other. 1 meter, 1 meter, that's 2 divided by 2, which is 1. The same thing here, we have got a 5 kilonewtons for 4 meters. So this is 4 times 5, which is 20 kilonewtons. So we shall have this like 20 kilonewton separated between the 4 meters. So if we divide by 2, that will be 2 meters. So this will be taken here as 2 meters. And this will be taken also this side as 2 meters. Okay, so that's it. Let's have our moments now. So I'm going to start with point A, taking moments about A. All right, so taking moments about A. That's moments about A. All right, so let's check what's happening here. From the A that we're talking about, D, which is another support, is moving in the anti-clockwise direction. Take note, it's vice versa. The way a clock is supposed to move in clockwise, there it's going in anti-clockwise, like this direction, back like this, back to A. So we shall work with the anti-clockwise moments here, the sum of the anti-clockwise moments being equal to the sum of the clockwise moments. So you can even list them out, the other forces that we have or the other moments. So this is anti-clockwise, okay? If we check the 10 kilonewton back to A, this will be a clockwise. So this will be clockwise. That's clockwise again, clockwise, clockwise, clockwise. So all these forces, they are going to move in clockwise. Okay, so you just have one in this case, which is the D. So D back to A here, that's force times distance. The distance, that's 3 plus 3, which is 6, plus 2, which is 8. So it's D times 8, which is equivalent. We multiply everything on the clockwise in this case. Okay, so let's take all the clockwise. That's from 10 here, 10 back to A, that's 10 times 1. So this will be 10 times 1 plus 35 back to A is 35 times 2. There's a distance of 2 meters here, 35 times 2. So that's 35 times 2 plus, we move on to 20. 20 back to A here. This is 3 plus 2, which is 5. So it's going to be 20 multiplied by 5 plus, we still have 20 here back to A. So remember, this is 3. Okay, let's start with here. From this point to this point is 2 plus 2 plus 3, which is 5. Then plus 3, which is 8, plus 2, which is 10. So it's 20 times 10. All right, so that's 20 times 10. Another one, which is 55. Remember, here we are at 10. At 20, here we are at 10. So we just have to add the remaining 2 meters. So 10 plus 2, that's 12. So this is going to be 55 times 12, like that. All right, so that's it. We are going to combine everything and calculate the value for D. All right, so that's 8 times D, which is 8D is equivalent to, I want to combine everything on the right-hand side. You're going to obtain 1,040. So dividing by 8, dividing by 8, that means we can obtain the value of D, which is going to give us 130 kilonewton. All right, so that's the value of D in this case, which is 130 kilonewton. So we have the value for D in this case, 130 kilonewton. All right, so using the same consideration, we are going to focus now from D to take moments about D so that we can have for A. All right, so let me just remove this part so that we can just have our calculations. Okay, let me do this. Okay, I just need to change here. All right, so I'm just gonna remove this part. All right, so here I'm gonna take moments about D in this case, this time. All right, so let's check now what is happening according to D. What is the relationship that we have between D and what? Between D and A. So this time we are from D, so this is not gonna work. Okay, so from D, we are going to see that A, as it moves to D, this is the movement of A here, is going to move this way, which is actually a clockwise. Remember, it is maintaining the way a clock moves facing to D. So this is clockwise. So I shall refer the sum of the clockwise moments in this case equal to the sum of the anti-clockwise moments. All right. So which other clockwise moments do we have? Okay, moving to D. Okay, so let's check this way. It's we actually the way anti-clockwise. This is, guys, please take note the movement. We say this is how a clock moves. So the moment you move this way, it's clockwise, anti-clockwise. So this 10 kilonewton referred back to D, it's in the anti-clockwise. So we've got anti-clockwise. The 35 here, it's anti-clockwise. That's 20 kilonewton moving this way, it's anti-clockwise. Okay, let's check 20 on this side, it's moving this way, which is clockwise. 55 is moving this way back to D, which is clockwise. Okay, so we have got a clockwise, and a clockwise. So we're going to combine these together. Okay, so let's have this from A back to D, that is A times 8. Remember 2 plus 3 plus 3, which is 8. So that's force times distance, which is 8 plus. We said we still have other in the clockwise, which is we are referring to 20 kilonewton. It's going in the clockwise. Okay, so it's 20 times a distance. What is the distance between 20 and D? Remember, we're referring back to D. So that's 20 times 2. So this will be 20 by 2. Okay, plus we still have another one, which is 55 back to D. Here we are referring to D. So it's 55 times 4. So this will be 55 multiplied by 4. All right, which is equal to, we are done with the clockwise, move on to the anti-clockwise. So back to D, we are going to start with the first one here, the anti-clockwise, which is at 20. So 20 here, moving to A to D, that is 3 meters. So it's 20 times 3. Okay, there's a distance of 3 meters there. So that's 20 times 3 plus 35 kilonewton back to D, that is 3 plus 3, which is 6. So it's 35 times 6 plus 10 is still anti-clockwise. So it's 10 times, remember at this point we are at 6. So we are going to add 1 meter because from 10 to this point is 1 meter. So 6 plus 1, that's 7. So it is going to be 10 times a distance of 7 meters. All right, so that's it. We can have the value of A from this. Okay, so if you combine everything, A times 8, that is 8A plus 20 times 2. In this case, I want us to combine everything so that at least it can help, because here we are going to have 20 times 2, which is 40, plus, in this case, 220. If you multiply, this will be 220. So if we add 240 plus 220, which is going to be 260. So 260 is equal to, so on this side, I want you to combine everything. You multiply, then you add, multiply, then you add, you're going to obtain 340. So 8a is equivalent to, if we transpose 260 to this side, that will be minus 260. That means we are going to obtain 80 in this case. So if we divide by 8, our A is going to be equivalent to 10. So that's a 10 kilonewton. All right. So we have the value of A in this case, which is a 10 kilonewton. So at A here, we are at 10 kilonewton. All right, so that is how we could have calculated. So you can even prove this by applying the sum of upward forces equal to the sum of what the downward forces. You add these forces, 10 plus 130, which is 140. So if you add 10 plus 35 plus 20 plus 20 plus 55, you must obtain 140. That is how you can actually prove that these two are the same. All right, so we are going to check for the other question in this case, which is very, very important. And I just want to apply this question down here. I have discovered that it's much better that way, so that we can properly understand, even though in exam, you're not supposed to do this for the shear force diagram, you're supposed to have this aside, not directly under the diagram, because this, look how the questions are. You cannot even, and by the way, you won't even have this. So you have to redraw it, so forth, for you to have the shear force diagram. Okay, so we are asked here to draw and fully label a shear force diagram using a suitable scale. In this case, I'm not going to apply any suitable scale. I'm just going to show you how you do it, but you're supposed to use a suitable scale, like you're going to use 5, 10, 15, or I don't know which scale are you going to use, but remember, this, we are going to take it direct from our original diagram that we had. Okay, so this is what we had from our original, so that you do not confuse. I'm just going to remove this so that it goes back originally to how it was before. All right, remember, this was a distributed load for 2 meters and this and that. The same thing here, this was a distributed load for 2 meters. So I'm just going to remove this so that I do not confuse you guys, so that you can understand how it was. So this is what we had. This was at 5 kilonewton per meter. All right, then our 4 meters does not change. Let me just move these parts here so that these are not important for now. Remember, this is not important for now. Also here, we had the 5 kilonewton per meter for the 2 meters and so forth. Okay, so this was our original diagram before. So we now need to have our shear force diagram, which is 2.22. All right, so let's do this, guys. All right, so this is 2.22. So our shear force diagram, we can actually take it from the horizontal. So I'm just going to continue with these lines. Okay, so let me insert a ruler so that we can see properly here. All right, I'm just gonna, I just hope it's going to be clear, guys. I just hope it's going to be clear, because I want you to see properly here. Maybe you skipped some of the videos that I've showed you, but I think I have also indicated from other previous videos how do you draw these diagrams, but just for the sake of those who didn't manage to see them. Okay, so this is what you're going to have in this case. We have drawn the horizontal line, which is representing our forces being our components being taken at what? At 0 from the horizontal. Okay, now I'm going to continue from A and so forth and so forth and so forth up to the end. All right, okay, what am I doing here? Okay, let me adjust. So guys, this thing of working with software, it's actually something else. It was easier those days when I was using pen and paper. But now it's complicated. Okay, but I just hope you're going to see what I'm trying to show you here. So here I'm just going to continue with the points A, B, C, and D, and so forth. Okay, so A, B, C, D, E, up to the last point. So we move on to C, and so on up to last point. All right, so we move on to D. So I'm just going to direct at those points. All right, direct from those points. Okay, then at E, like that, direct also at E. All right, so this is what we have, guys. Like I said, we started at 0 in this case. That is the horizontal line. It's representing at 0. So to meaning to say that everything that we are talking about is at 0. All right, so according to our force, let's check what is happening at A. This is at 0 corresponding with A, okay? So at A, what is happening is that if you are to check here, at A, we've got a support. That is the only thing that we have at A. There's a support, okay? Before the distributed load, we are talking about a support, which is of 10 kilonewton. Okay, so what does it mean? A support, remember, guys, is a positive. Always, if you're dealing support, know that it's a carries a positive and it's going up. So which means at A, which is at 0, okay, at the starting point at 0, we are going to add the 10 kilonewton is the support. So if we add 10, we are going to remain at 10 kilonewton. So we're going up to 10. So like I was saying, if you use a scale of 5, 10, 15, 20, we are going to count 5, 10. At 10, that is where you mark your point. So let's say in this case, according to my scale, my 10 is at this point here. All right. So that means I'm going to join direct from 0 to 10. It's a support. So a support, remember, it goes up direct as it is. Okay, so here I'm going to draw straight to my 10 at this point. Okay, so let's say this is where I have my 10 kilonewton at this point. All right, so that's from 0 to 10. Then from in between A and B, take note, you are no longer working. Okay, don't separate. We could have done this, but it's going to have a lot of things. I talked about this in other videos, but I want you to check here. Instead of having this separated in between this to say we distribute again, no, let's distribute this across. It's distributed across the 2 meters from A up to point B. So from A to B, we have got 2 meters. So we're going to multiply 5 times 2. So that means a distributed load, remember, it's supposed to be a slanted line like this. So you're going to subtract, it's a negative, it's going down. So this is going to be at 10. Remember, we are at 10 kilonewton right now. So this is going to be at 10 minus 5 times 2, the 5 kilonewton times the distance of 2 meters from A to B, which is going to give us a 0. So this is going back at 0. So that is at 0 at this point. So we're going to mark a 0. Direct at B, which is at this point, that is where we have at 0 on the horizontal, direct on the line. So we're going to join a slanted line from 10 up to 0 like this. Okay, so this is just a slanted line from 10 up to 0. So this one was going down to 0 like this. All right, so this is where we are now at this point. All right, so I just hope you understand what happened in this case. It's a distributed load, so you subtract the product of what? 5 kilonewton times the number of meters, which is 5. Now you are at B. Okay, at B, there is a point load which is facing down again. A point load, you're going to subtract, but this one, it goes straight. A support, it goes up straight. A point load, it goes down straight. It's only a distributed, which is slanted like this, which slants like what we have, like that one. Okay, so at 0, we are going to subtract 35 kilonewton, which is our point load. So 0 minus 35, that will be at negative 35 kilonewton. So I'm going down to negative 35 according to the scale, okay? So according to the scale, let's say my negative 35 is at this point. This is where I'm going to mark my negative 35 kilonewton, then I join from this point. So you use a suitable scale, guys, like I said. Okay, so this is what I'm gonna do. Join up to this point. This is your negative 35 at this point. All right, so we're at B now. So let's check what is happening between B and C. Between B and C, there's nothing. We do not have just a distance of 3. So I'm just going to move 3 meters up to C. So you continue straight from that point. There's nothing that you're going to affect. In this case, you just move straight to this point. Okay, so here, let me just add some of these lines. Okay, so here we are going to move straight, which means we are still at negative 35 kilonewton. We are still at this point of negative 35. So this is where we are now. Still we at negative 35 because this we're just moving straight. So we are still at negative 35 kilonewton at point what? At point C. All right, now at point C, if you are to check here, there is a point load again at point C. We've got a point load of 20 kilonewton, which is a negative. So we're going to remember, we are still at negative 35. So we are going to subtract point load negative 35, negative 20, which is at negative 50. That's negative 20. So this will be negative 55. All right, kilonewton. So we are going down to negative 55 kilonewton. All right. So this is a point load. So it goes down straight to negative 55. Okay. So that's according to my scale. Let's say this is where I'm having my negative 55 kilonewton at this point. Okay. So I'm going to join straight down to negative 55. All right. So that's to negative 55 straight like this. All right, so we are going to join up to this point. All right, so this is where we have our negative 55 at C. So let's check what is happening from this C to D. From C to D, there is nothing also here, just a normal distance of 3 meters. So you move your 3 meters direct to D. All right, so you're going to move 3 meters, that is a straight horizontal in this case. Okay, so my ruler has disappeared. I can't remove from where it is now. Let me set another one. Sorry for that. All right, so like I said, I'm going to move direct 3 meters to D. Okay, so this is according to your scale. You move straight to D. Okay, meaning to say we haven't changed anything in this case. We are still at the point of negative 55. We haven't changed. We just moved straight as it is. So at this point, we are still at negative 55 kilonewton. That is where we are at point D. But at D, there is something that is very, very important that we have there. We have got a support, the D of 130 kilonewton at point D, which is going up. Remember, it's a positive, so we're going to add 130, where we are at negative 55. So at negative 55, if we add 130, this is going to give us 75 kilonewtons. So we're going up to 75. Okay, so this is going up straight to 75. So according to your scale, maybe this is where you have your 75 at this point. Okay, so this is just an assumption according to me, but you're supposed to take this directive according to the points that you are given. So this is exactly where I'm having my 75 according to me, guys. This is where I'm gonna have my 75 kilonewton at D. Okay, so I've moved the one for D. Let's check what is happening between D and E. Okay, between D and E, this is what we have. There is a distributed load, okay, of 5 kilonewton per meter for the 4 meters. So which means at 75 kilonewton, we are going to subtract the distributed load of 5 kilonewton for the 4 meters that we are given, which is going to be 75 minus 5 times, so which is now at 55. So this is going to be at 55. So remember, a distributed load is going to be slanted like this. So this is going to slant up to 55. So let's say, according to my scale, 55 is going to be above this 10. So maybe this is where I'm going to have my 55 at this point. So I'm going to mark this point. Then I join from 75 to 55. Okay, so this is what I'm going to do here. 75 to 55 like this. All right. So these are the points. I'm going to join these points, 75 to 55. Now, if we are to check here, we are at 55. This is the point here at 55 kilonewton. All right. This is at direct at point E. We have moved this. We are now at point E. At point E, there's a point load of 55 kilonewton, which is facing down. So we are going to subtract 55. So where we are at 55 kilonewton, if we subtract 55, we are going to be at 0. And it's a point load, it goes straight to 0. So this one is going to go straight up to 0. That is to the horizontal line. That is our 0 point here. That's at 0 kilonewton. So we are going to have a closed figure at the end. That's our shear force diagram. Okay, so that is what we had, guys. And these are the major points that you're going to have from 0 to 10, back to 0 in this case. So this was back to 0 kilonewton. It went to negative 35, maintained, negative 35, went to negative 55, maintained. The negative 55 goes up to 75, down to 55, and down at 0. Okay, so this is what our diagram was going to be like. Okay, so that's what we had, guys. And you can check it's fair enough as to have the 4 marks for this shear force diagram. Okay, and everything that was actually 12 marks on moments from this question paper of November 2020. So that's what we had, guys, for Meson African Motives, working on engineering science N3 till we meet again.